Week 2. Let's get started. We're going to look at the aspects of a distribution. So the distribution, that word, distribution, is just basically looking at how your data is distributed. So there are three main components to this, and each of those have some subcomponents. There is the shape, the location, and the spread. We'll go further into each of these. When you're looking at the shape, this allows you to better understand the data from a visual perspective. So there are different ways of looking at the shape. There's stem plots, frequency tables, box plots, histograms, bar graphs, pie charts, line graphs. We're going to briefly go over each of these and just to look at them before moving forward and to go into further detail. So first off is stem plot. This isn't something that you're really going to do all the time if you really start to collecting data, but it is a good practice and a better understanding of what a stem plot is. Now, I'm not going to make you do these a lot because software does it for you, but it's good to look at what the different types of stem plots are. So if you notice that there is a vertical stem plot, which is going from top down, it always starts off with the lowest numbers first, and then the highest numbers are at the bottom. Now, generally, you're not going to see graphs that are kind of to the side because you kind of have to tilt your head. So what they're usually kind of turned into are histograms, which kind of looks more like a horizontal stem plot. So on the right is a horizontal stem plot. So just to give you an idea of two different types. So what are these numbers that we're looking at here? Well, these are the exact same stem plots, just rotated. The one on the left, it starts off with basically at the tens values of 0, like what is that 0 and 5? So in other words, that very top number on the vertical and on the very left is going to be 5. There's just 5 there. And then the next one would be 11 because you're going into the 10th number, and that there's a 1 there, so that would be 1, so that would be 11. If you go to the 2, now we're in the 20s, now you have 21, 24, 27, 28, and then we have a 30, we have a 42, and then a what? 50 and 52. Looking at this at a different angle for frequency tables. Frequency tables are, we're just kind of jumping just to a quick little other ship of frequency tables, and just knowing that when you have, say, different classes or ranges and how you are basically dividing your data sets, it can look something like this. So say you were to collect data on different school children, and you started from the ages of 3 to 19. Well, if you divided them into preschool, elementary, middle school, and high school, you could make a frequency table to get a better understanding, a better view of what your data looks like. So in this example, we only have 11 preschoolers versus 469 elementary school students versus just 100 middle school and just 74 high school students. The relative frequency, you could also just consider it frequency, is the percentage in which that frequency is related to the other classes. So, for example, 71% of this data set, this mock data set, is of elementary school students. And well, we only have 1.7% of preschool students. Now, if you go to the right, the very right column, we have the cumulative frequency. So it's always good to put everything in order first, and that way a cumulative frequency would make more sense. So you can look at, the total, the sum total, based on, the higher age ranges you go. So for instance, if you just start off with just preschoolers, the cumulative frequency is just 1.7. You haven't added anything than just the relative frequency. Now, your cumulative frequency, once you get to an elementary school, now you're looking at elementary and preschool, so you're adding 71.7% to that 1.7%. If you add on the middle schoolers, it adds 15.3%, and if you add the seniors, it adds 11.3%. So that totals into 100 for both the relative and cumulative frequency. This basically, you know, I don't want to say it's common sense, but it is something that when you look at it for long enough, you can kind of understand kind of the math. So say, you know, I was to delete the 15.3% from the junior high relative frequency, you could do the math to figure out what actually is that number. It's not a bad question to ask. Here's another example, and this is actually the example of a frequency table based on that stem plot that we were looking at earlier. So remember that there was just one thing within the 0 to 10 range. Now, in order to keep everything properly divided, this goes from 0 to 9.9%. That way the next class can be divided straight at 10. So it's just easier for everyone to just kind of have that starting off with a 0 number and then ending with a 9. And within looking at this, you can just tell that the frequency is rather small until you get to the ages of 20 through 29, and then it drops off again, and then you get at least 2 in the 50 to 59. So again, we have the relative frequency in the middle, and then cumulative frequency on the side. We're going to talk about box plots, but this is just what's also called a box and whisker. And basically, this is a great way to look at the data kind of from a top-down view and to see where most of the data is. This will also help you see if there's any outliers within it, but we will go into that a little bit further. Histograms. Histograms are basically bar charts with continuous numbers. So remember, continuous can just kind of go on forever and are reserved for displaying frequencies associated with quantitative variables. That's a little bit different than the bar chart, which these are used to correspond basically the height of these frequencies and or relative frequencies. Pie charts are used for percentages, and line graphs are for basically allows you to show continuous data. It could be trends or maybe over time, and this is good, you know, going from, you know, it can either be comparing two different groups, but also looking at, you know, maybe the same group for an X amount of time. So this is a big data visual that we have right here. I mean, to look at this and be like, yeah, okay, that looks nice. To really think about how much data was needed to collect over the years, I mean, this is, if you look at it, that's a 16-year data collection. So there's a lot of data that was organized just to get this simple little graph. Each of these each type of graph really goes to certain levels of what sort of data sets you have. So if you have certain variables that are nominal, you're going to use frequency tables, bar graphs, and pie charts because that goes well. But ordinal is going to look a little, you know, it's more flexible. You can have a stem and leaf as you're able to actually have something that's scaled versus a stem and leaf. You can't really do that with a nominal. A nominal is categorical, so it doesn't really fit well. So here we are entering the stem plots. So stem plots are, I like to consider them kind of the training wheels of data. What do they look like and what do they even do? So this is the same one that we saw earlier, and then here comes the same stem plot on a horizontal scale. You can kind of tilt your head to the right to help yourself look at the first one, and you realize it's actually the exact same thing. Here it is again. Actually, is this the same one? Let me just double check that. No, it's not. That is a different one. So this is actually something that we will do in class, and just open this up, and you're going to practice listing the data into an orderly rank, because it's always good to have everything organized. And we're going to make our own stem and leaf with it. Yay! All right, so this is kind of what it's going to start to look like. You're going to put, starting from 0 in the top left corner, and then you go down 1, 2, 3, 4, 5. You can put a little space there, and then you can start adding them up. And this is what the final result looks like when you're organizing that data set down there into a vertical stem plot. And that's what it looks like horizontally, again. Within this, we can now start to see the shape. And that is the pattern in which the data looks like. This was used as a skyline silhouette. Sure, we can consider it a silhouette. From very far away, it's like, wow, that's really pretty. Everything just kind of looks, bloggy out there. What we're looking at here when we're looking at the shape is the symmetry, the modality, the kurtosis, and the outliers. We'll go into each of those. So symmetry is looking at how much of the data maybe tends to be on one side versus the other side versus maybe not at all, which would be symmetrical. And that's what we want. And so we'll go further into each of these, but we have modality, which is looking at the number of peaks. So if there's a lot in a certain area, say you collect a bunch of data of individuals of all ages, and you notice that there's 2 peaks, and that would be, the modality would be, say at a young age you have a bunch of 20-year-olds and then a bunch of 80-year-olds, but everything else is really low. Well, then now you have 2 peaks. You have kurtosis, which is the width of the tails, and then you have the outliers, and the outliers are exactly what they sound like. They're kind of outliers. They're kind of out on the edge of the data set. So we look at symmetry to determine if the data is normally distributed, and that satisfies the assumptions for parametric inferential statistics. It's a lot of words to say, is the data organized enough that we can do certain statistical analysis? In this sense, it's parametric inferential statistics. We'll get into those bigger words later on, but just know, when it's symmetrical, everything is so much better. So we always want to aim for symmetrical data. Here it is as a histogram. And what we have here are scores, what looks like, and we have the number of individuals who made those scores. So we can just say that this is a, I don't know, an ACT or something. I don't know what goes to 140. That seems like a very arbitrary number. But it gives you an idea that you can kind of say that this histogram looks rather symmetrical. So this is this would be a nice data set to work with. Now, when it's not symmetrical, it can be skewed, and there are multiple terms for this. So I apologize. So we're going to try to stay consistent, but I swear either the book or this PowerPoint kind of goes one way or the other, and I am sometimes helpless on it. So I'm going to do my best. So here's how I want you to remember skewness. So with positive skew, everything is there is more frequent. The frequency is higher on lower numbers. And so think about it in the sense with this positive skew. If you collected data of all these different ages, a positive skew would be a bunch of, you basically collected data from a bunch of younger people rather than older people. In contrast, a negative skew is going to be the opposite way. So say you collected data of ages and you collected a bunch of 80-year-olds rather than 20-year-olds. Then you're going to have a negative skew. So the way I remember this is actually I just remember one, and then by deductive reasoning I remember the other one. So you have a positive skew. If you notice, if you were to draw like a capital P, it would fit actually like kind of nice in that underneath that little lip there, and I'll probably draw this in class. And so that always helps me just think about, the P is up at the very left, it's a capital letter, so that means it's on the very left. That makes more sense than putting it on the very right of anything. And so if I know where the positive skew is, then I know what a negative skew is. It's a quick way to think about it, but just remember that skewness is related to symmetry. And if you have a positive or negative skewed data set, it is not symmetrical. It can be a little bit of both. It kind of depends on the data. So here is just another example of it. You can notice that with the symmetrical data, you're going to have the mean and the median actually the same. But when you have a positive skew, you're actually going to have a higher median and rather than a mean. And vice versa, with a negative skew, you're going to have a higher median than a mean. Did I say that right? Yes. So actually, and with this, one is always going to be bigger than the other. And just know that when you have a different mean and a different median, it's going to be skewed. That means it's skewed. And then there's that. I always forget about these things. I apologize. See, then they use right skewed and left skewed, but then we're going to go back to positive skewed. So I'm sorry. I'm doing my best. With shape, you can really start to see, what sort of skew this is, positive or negative. Hopefully you thought positive, or you're texting. I don't know what you're doing. This is a video. Again, modality is looking at the number of peaks. So a unimodal would mean just basically there's one good peak, and so basically the data goes up and then it falls right back down. Whereas bimodal, which is two, other than unimodal, you're going to have multiple peaks, going back to that example of 20-year-olds and 80-year-olds. That's what a bimodal would look like. Again, we kind of want to aim for that unimodal. It only has one peak and everything is clustered right at the top. It's nice for us, nice with the data. You can mix and match these things. Things can be symmetrical and they can be uniform, or they could be asymmetrical, which means non-symmetrical, and it can have multiple modality points. So mix and match, the data is going to be different. Moving on to kurtosis. Kurtosis is this steepness. It tells us about the tails of the distribution. So it's not the peakness or the flatness. It's not about how high it goes up, but really how much it's spread along the tails. And the tails are at the end of, say, the bell curve. And with that, a low kurtosis in a data set means that there's really not many outliers, which is often really good. Okay. So there are so many different types of statistics, but we're going to kind of brush up on mainly two of them within this course. We have descriptive statistics, which is kind of just like basically what is the stat sheet of an individual, the overall arching basic information about the data set. And then there's inferential statistics, which is, really taking in hypothesis testing. And we're going to do that later on in the semester. But for now, just know that there are two different types that we're really going to dive into. So with descriptive statistics, and that's what we're really focusing on in this class, or in this video, is when we're looking at the central location, so that's the mean, median, and mode, as well as the spread. So how wide is this data set? And then once we really kind of got the descriptives down, then we're able to go into those inferential statistics. Those are kind of like the bosses to battle. That's where you get the ANOVAs and the t-tests and all the fun ones that we can do with data. Yeah. Okay. I'm going to let's just think about what is the difference between differential or inferential. So with descriptive statistics, it's like the overall stuff. We're just collecting stuff. So if I just collected some information off of you right now and I just tallied it up into frequencies, that's going to be a descriptive. So here's a question for you. How many university students experience high stress levels? So if you go around and you ask how many students are experiencing high stress levels, are you making an inference or are you finding descriptives? The answer is descriptives, because you're just collecting, basically yes and no, and how many students. You can maybe divide that into like age or something. But in general, you're just actually collecting like kind of a yes or no. How many students are experiencing high stress levels? How do you define that? Number two, do non-binary students experience higher stress levels than non-binary students? So now we're looking at the exact same thing of higher stress levels, but we're actually taking that data set and we're dividing it. We're splitting it off into chunks, and we're looking at those chunks and looking at what the differences are. So would that be descriptive still? It's inferential. Let's try two more. What strategies are used by first-year university students? How would you go about this? Well, you might go around and you might ask, hey, what are your strategies? And then you start tally up what they like to do. Oh, I like to write on my hand. Oh, I just cheat. Oh, I just don't even do any work. Oh, well, actually, I use Google Chrome for everything. I don't know. Are you making any inferences? No. So this would be descriptive. You're just kind of, again, checking some boxes to see what students are doing. Is there a relationship between university students' studying strategies and academic results? So now you're able to take all of that information that they have that, how they study, and then you're actually going to look at what their grades are at the end of the semester. Now we're able to actually really start to compare, and we're able to make inferences. So, with descriptive statistics, it's also considered like summary statistics. You're looking at the mean, median, and mode. So we have the idea of what the shape looks like, and so now this is more diving into what's inside of that shape. And then we also have the spread. So how wide, how far apart your data your range is. Starting off with central location, we have mean, median, and mode. You know what that means? We're back in high school. Yay! Moving on. Okay, so just to cover kind of like what you should know when it comes to terms that you'll see in the book. We have an N, which usually means sample size, and that's usually lowercase n. If it's a capital N, then that's usually like a population number. Then you have X, which is the variable. And a good example that I have here is just like the ages of the subject. And then you have the value, you have the xi, which is the value of the individual for the variable. And so if you look down here at the bottom, let's just follow this for a second. So we have this data set right here, all these numbers right here. And this is actually the number that we were looking at earlier. These numbers were. So how many total what's our sample size here? Well, we have 10. We have 10 different numbers. The X is the age variable. So this is an X. It could be X equals 21, X equals 42, X equals 5, X equals 11. And that is within itself, by you dividing it into different areas, then you have X1, X2, X3, X4, X5, X6, all the way to X10. So this is just a way to, if you need to further, it's going to help out with formulas, but if you need to, basically split apart each data point to itself. And then we have sigma, which is the sum of all values. So you basically add everything up, and that is your sigma, or your sum. With the central location, it's basically finding the balancing point. So if you were to put all of these data points onto a balancing board, you need to find out where the mean is, and basically that is the central point in which you can actually make everything balanced on a certain number. You are probably familiar with how to find that, and the mean is also called the average. And this is very traditional in most things. It's highly susceptible, though, to outliers and skewness. And basically what you do is you add all the numbers and you divide it by the n. And that is also called the x bar, or the sum is. So this is the formula for it. All nice and pretty, right? Yeah, okay, it's really not that bad when you look at this. You have the sum right here, or you have the mean, which is x bar, which is 1 over n, and that is and then you add in the accumulation of all the x's. Same exact thing. This is saying when it comes to back here is I'm going to add these 10 numbers up, which is 290, and then I'm going to divide it by 10. That's it. So is this something that you really need to know, and like when you're out there in the field, like I need to know what these are? Yes. However, this kind of throws you off because there's calculators that do that. All right. So we're moving forward with it. We have 21, 42, 5, 11, 30, 50, 28, 27, 24, and 52. We add those up to 90, and what do we get? What's our average? 29. I don't even think you needed a calculator for that, did you? Look at that. All right. With that symbol of x bar, which is nice and pretty, right? There's also the exact same thing, which is a mu, which is the population mean. So this is a way to actually differentiate certain samples to population. So what a population is basically this, like the larger population. So think of like the UNC student population. If you actually to collect some sort of data out of them, you would and get their average, you would use a mu. However, if you took a sample from that, then that's when you would use an X bar. With the median is basically, if you were to have a string of numbers, it is where on that just linear scale, where is the middle? So sometimes it might not even be the exact number, it might be, you know, right in between. So for example, with the median of our numbers, we have 27.5. So if I was to count 1, 2, 3, 4, 5, it's right in the middle. Then we have 6, 7, 8, 9, 10. So the way to find the median, it's super simple. Whatever your n is, which here it's 10, you add 1, divide by 2. So 11 divided by 2 is 5.5. It's right here. And that is 27.5. All right, so practice what the median is for this. For this, I want this to be done in class, so I'm just going to kind of skip over that. That's all right with you. Is that all right with you? That's all right with you. The median is more robust or more resistant to skewness in comparison to means. So we're going to go over this further, but just remember, like, there's a lot of times where you shouldn't just know the average of something, you should know the median of something. And I'm pretty sure we go over it. Yep, we sure do in the next slide. Haha. So you can do this on your own, but we are going to do this in class. So let's say you have 10 workers or 9 workers and there's a president. The 9 workers make $10,000 a year and the president makes $100,000 a year. Look at the average and look at the median and look at the difference and see which one was more susceptible to skewness. Analyze that data. Then we have the mode. This isn't something that we're really going to go, it's really not that useful all the time other than seeing what has been repeated. And so the mode is in how many times is the most used number. So it could be, in this data set, the mode is 7 because there's 3 7s. If you took away those 7s, it would be 8 because there's 2 8s. There's no mode in that next example of 4, 6, 7, 8. So there's no mode. All right, yes, we know this. Moving forward. Now, spread is the variability of the data points. This can be looked at within our context 2 different ways. We have the range and interquartile range, and then we have the variance and standard deviation. So what happens to the spread when you remove an outlier? Well, let's look at it. These are box and whisker plots. Or this is one box and whisker plot. So what we have here is basically this would be an outlier right here. So if you removed that outlier, then all you would have is this. So therefore, which one has a greater spread? It's once you remove the outlier. That's what happens. The spread decreases, which is good at times. Okay, although suited for some purposes, the range is not a very good general measure of spread. And the range is basically maximum minus the minimum. So you take the highest number and you minus the minimum. Now, it's not always the best for anything, but it gives you an idea of basically your range, and that can also help you in organizing your data. And in addition, it's also unlikely to capture both the maximum and minimum in a population. So it has a tendency to underestimate an actual population's range. So in other words, if I was to go out into UNC and collect all the ages of all the students, and say I just did my best at it, I would only have a sample, right? And I am not actually able to collect everyone's data. Well, then that might not actually be true to the original number, because there might be an 82-year-old, which I think there's like an 82-year-old something that's on campus that's taking classes. What if I didn't get them in my sample? Well, then that would change my range drastically moving forward. So it's always good to know the spread, and so doing the range is something well worth just practicing within data. What just happened there? Okay. So two distributions can be quite different, yet they can have the same mean. So notice this example, site 1 and site 2 have the same mean. However, site 1 has a ridiculous outlier that's way out there. So this goes back to the mean. You need to look at the mean, you need to look at the median, you need to look at the range, you need to look at the mode, looking at everything just to get a better feel. That's kind of like you're putting on certain goggles or certain spectacles to look at the data sets just to get a better understanding of it. Here are two differences within a spread of two different population. The spread on population 2 is much wider than what we have in population 1. Which one would be better off if you wanted to collect data in a parametric world? It would be population 1. Is there anything else I want to say on this one? No, we're good. Interquartile range. So we're looking at quartiles. So basically, we are looking at quartiles and it provides a way of looking at the spread, and it also helps us set us up for box plots. So I'm putting the data set that we've been using, and what we look at for an interquartile range is we need to look at Q1, Q3, and Q3 minus Q1. So within this, we always find, in the book, it provides we have a Q0, Q1, 2, 3, 4, 5. And with 0, that's the lowest number, Q0. Q5 is going to be the highest number, or Q4 is going to be the highest number in this one. Should be, yeah, that makes sense. Yeah, I'm sorry, I meant to say up to Q5. There's 5 of them, but it goes up to Q4. Okay, I see where I messed up there. So 52 is the highest, so that would go to Q4. Q0 is at 5. We have the median. How do we find that? It's n plus 1 divided by 2. So we have it right there. And then Q1 it cuts off the lower half of wherever the median is. So if you were to count, so from 27 to 5, we go 1, 2, 3, 4, 5. Same here, 1, 2, 3, 4, 5. What's right in the middle? It's 21 and 42. This is the 5-point summary. So again, same thing. I kind of jumped the gun. It's always because I always forget what's next, and I always prep myself for it, so please excuse me. So we have the minimum. We have Q1, which is the 25th percentile, or the hinge. We have the median. We have Q3, which is the 75th percentile, and then Q4, that is the maximum. All right, let's create some box plots. What does that look like for us? I want you to create the data set that we have here and turn it into a box plot. That's what it looks like. If you want to go into more detail, I would say just for time, let's move forward. More with box plots. This is basically the whole thing in a nice nutshell again. Here's a second example that we are going to do in class. It's going to look a little bit differently. If you'd like to compare them. All right. And with that, we come to standard deviation and variance. So standard deviation and variance, that's something that, personally for me, I was always kind of like, what is this? What am I trying to get to? But it's just the spread. It's to help you understand, from a very concrete mathematical formula, what the spread looks like of your data set. So in my notes, I'm going to read it, but it says the variance and the standard deviation are the most common measures of spread. IQR is also a common measure. I suggest that we practice this a lot, and so that's what we're going to do, just because finding the deviation and how much things deviate, just practicing saying it and knowing it, how to locate it, is something that would be really essential when you are writing a paper, manuscript, or looking at data. So within this example here, our deviation is whatever from the lowest or highest number, how much those numbers from that point to the mean, how much it deviates from it. So in this example, if the mean is 36, well, it can deviate all the way minus 4 points, based on this data set, because we have a 32. What you take is the mean minus the lowest number, so whichever number that is. Oh, I'm sorry, I mixed that up. You take xi, so in this case it's 32, minus the mean, we have negative 4. We do it the opposite way. We have 40 minus 36, we have 4. So the deviation that we have here for at least these 2 points is negative 4 and 4. If you were to do 33, it would be negative 3. If you were to do 37, which is right here, it would be 1, but there is no 37. I don't know why they even put that one in there. So deviation is basically that one number minus the mean. And then in order to get to the standard deviation, we would square that for each of the numbers, and then we would put an n divided, or an n minus 1 to get the variance, and that actually gives us a full detail, full spectrum. And we'll use variance a lot, and it comes in different shapes and sizes, but just lack of a better word, variances vary. But in order to get the variance, then you can get the standard deviation by just squaring whatever your variance is. I had to think about that one. So what we're looking at right here is the sum of squares. This is, or also known as like SS. And this is a standard deviation in order to find that. Now, here's the nice part. You don't need to memorize any of this because computers do it for you. So that's why I'm just kind of showing it to you, but then we're moving on. It is a lowercase s. That is for a sample standard deviation. However, for a population standard deviation, it is this lowercase sigma. And you can actually write one in the computer. I try to always add them so that way you always have access. You can always copy and paste them. So fun facts, deviations always sum up to 0 because you're taking everything, that's less than the mean as well as what's more than the mean, and they always, all that deviation, when they sum up, it equals to 0 because you find yourself right back in the middle. Same units. What else did I want to say here? Standard deviations are useful when making comparison. So the greater the variability within a group, the larger its standard deviation. So a wider spread, greater standard deviation. Lesser spread, smaller standard deviation. Smaller standard deviation, depending on what you're looking at, can be really nice. You're saying, oh wow, the data I collected, there's really not that much wiggle room. There's not that much variance out of that, is what you could hear and or say. This is something that when I was in school, we constantly did, and we did a ton of it. And as much as I would love to practice this and do it, I see it as kind of a waste of time, primarily because there's calculators for that and software. So, but here it is in all of its glory. You can practice it at home. I'm not going to make you do that. But once you do all of this, then you have 2 extra parts to do. You have to find the variance, and you can only find that once you get the sum of squares, which is in the previous slide. And then you get the standard deviation by squaring that, by square rooting that, I meant to say. Whew. The standard deviation can be used to describe the percentage of the data points that will fall within certain ranges. So these ranges are commonly found with a normal distribution of 68, 95, 99.7. This is the normal rule. And the other rule is I've always messed up this name, but Chebyshev's rule. Okay, it always throws me off. And again, this is for normal distribution only, so it has to be what? Symmetrical or asymmetrical? All right, we are coming down to the end of it. So when you're choosing summary statistics, you always report the sample size, and a measure of central location and a spread. The mean should be accompanied by the standard deviation. The median should be accompanied by the interquartile ranges. So we should really work on practicing that. And with data sets, we're going to have fun with that. Outside of that, I mean, we go into more detail. Obviously, I give you this like table right here, right? And you need to know that nominal or categorical, they can use they really use counts and frequencies, proportions, which is percentages in a different number or without the percentage sign. You have the mode, but you won't use the median because these are categorical, so you can't really take different stages of something, for instance, or different sections and find the median or the mean between those. But for intervals and ratios, you can, because those are continuous. So that homework is actually not true. So I'm actually done. I finished this. This is my first time ever trying it. God, I hope this helps. I really do. And my mouth is dry, and I've been going at it for 45 minutes.